Heron's formula for a triangular area. So the theorem states that a triangle with side lengths A, B, and C, the triangular area represented by K is equal to the square root of the whole quantity S times the quantity S minus A times the quantity S minus B times the quantity S minus C, where S is equal to 1/2 the quantity A plus B plus C, which is the so-called semi-perimeter of the triangle. So using figure 5.3, we use the side measurement lengths to substitute in for to find the value of S. So we get 1/2 times the quantity is equal to 34. So let me plug in our value for S into our equation for K and get the result of 204, which would be the triangular area. And then when using this formula in comparison to the normal A equals 1/2 base times height, all we need to find is the 3 side lengths and not the altitude. Proposition 1 for the theorem states that the bisectors of the angles of a triangle meet at a point in the center of the triangle's inscribed circle. Proposition 2 states that in a right-angled triangle, if a perpendicular is drawn from the right angle to the base of the triangles on each side of it are similar to the triangles to one another, which means that triangle A, B, and C in the image to the right is similar to triangle GAC, which is similar to triangle DBA. Proposition 3 states that in a right triangle, the midpoint of the hypotenuse is equidistant from the 3 vertices. So to prove that, we use figure 5.4, also from the book. We bisect side AB at point D and construct segment DM perpendicular to segment AB. Drawing segment MA, we claim that triangle MAD is congruent to triangle MBD, because segment AD is equal to segment BD, angle ADM is equal to angle DBM, and segment DM is, of course, equal to DM. Using side angle side, we know that segment MA is equal to segment MB, and the angle MAD is equal to MBD. Therefore, angle AMC equals 1 right angle minus angle MBD, which is also equal to 1 right angle minus angle MAD, again equal to AMC. Triangle MAC is an isosceles triangle now, so segment MA is equal to segment MC, and we already know that segment MA is equal to MB. Therefore, the midpoint of the hypotenuse, point M, is equidistant from all 3 vertices A, B, and C. Proposition 4 states that if ARBO is an equilateral, HBO is a quadrilateral with diagonals AB and OH, and if angle HAB and HOB are right, then the circle can be drawn passing through the vertices A, O, B, and H. And to prove this, we build off proposition 3. So we bisect BH at point M, and we see the point M is the midpoint of the hypotenuse of both right triangles BAH and right triangle BOH. Going off the last proof, this means that point M is equidistant from points A, O, B, and H. So the circle centered at point M and having a radius of MH will pass through all 4 quadrilateral vertices. Proposition 5 is a lot shorter, and going off the image to the right, it states that the opposite angles of a cyclic quadrilateral sum to the 2 right angles, which is 90 plus 90 equals 180. Into the theorem, part A. It's broken into 3 parts. Part A says, he began with inscribing a circle within the triangle, letting O be the center of the inscribed circle, and denoting the radius by R. We see that segment OD is equal to segment OE is equal to segment OF is equal to the radius, as shown in the figure to the right. Now we apply the simple formula for triangle area below to get that, to get the image in the middle. So thus K, the area of triangle ABC, is equal to the area of triangle AOB plus the area of triangle BOC plus the area of COA. Or K is equal to 1/2 CR plus 1/2 AR plus 1/2 BRs, which can then be simplified down into R is equal to the quantity A plus B plus C over 2, which is equal to RS. So in the end, K is equal to RS. Theorem part B states that, looking at the same figure, 5.6 again, the triangle MAC has been decomposed into 3 pairs of congruent triangles. So AOD is congruent to triangle AOF, triangle BOD is congruent to triangle BOE, triangle COE is congruent to triangle COF, where in each of the congruencies, we use angle side. which gives us the corresponding parts of segment AD is equal to segment AP, segment BD is equal to BE, and segment CE is equal to CF. And angle AOG is equal to angle AOF, angle BOD is equal to BOE, and so on. So then he decided to extend the triangle's base from AB all the way to point G, where the value for AG is equal to the value of segment CE. And then argues that segment BG is equal to segment BD plus BA plus AG, which is also equal to BD plus AD plus CE via construction. Simplify that all down into 1/2 times the quantity 2BD plus 2AD plus 2CE. Simplify it all the way down, continuing, we eventually get it down to BG is equal to S. So knowing that BG is equal to S, we can then derive that S minus C is equal to the segment BG minus BA is equal to AG. And S minus B comes out to be equal to BD. And so on to S minus A is equal to segment AD. Here part C is a lot longer. It's the ending. So now looking at figure 5.7, we drew OL, the segment OL perpendicular segment OB, cutting AB at point K. Then we construct AM, the segment AM perpendicular to segment AB, meeting segment OL at point H, and finally he drew segment BH. The resultant quadrilateral is the same quadrilateral from proposition 4, and is a cyclic quadrilateral as in proposition 5. So we know that the opposite angles sum to two right angles. So now examining the angles about the incenter, by congruence from part B, these reduce into 3 pairs of equal angles, so that 2 times alpha plus 2 times beta times 2 times gamma equals 4 right angles, or alpha plus beta plus gamma equals 2 right angles. But beta plus gamma is equal to angle AOB. So theta plus AOB must be equal to 2 right angles, which is equal to AHB plus AOB, which makes alpha equal to angle AHB, which doesn't seem to matter much at the moment, but he then observes that triangle COF is similar to triangle BHA, and gives you that CFO and BHA are both right angles. So then we derive the proportion to the bottom center. And then up into the part of the note, we get segment CF is equal to segment AD, and segment OF is equal to R. We then get the following equation. So then he noted that triangle KAH is similar to KDO, and that both of those angles are right, the vertical angles are equal, which gives you the equation next. Continuing, combining the last 2 steps, you get segment AB over segment AG is equal to AK over KD. Then he looked at triangle BOK with the altitude OD, which is also the radius. And by proposition 2, we know that the 2 triangles are similar, so therefore we end up with the following equation. Then he adds 1 to each side, in the form of AG over AG to the left and KD over KD to the right, and simplify it down to get BG over AG equals AD over KD. Finally, he then multiplies the left side by BG over BG and the right side over BD over BD, following, which leaves us with some of your substitution, which leaves us with the square root, RS equals the square root of the quantity S times S minus A times S quantity S minus B times quantity S minus C. And since RS is equal to K, we are then left with his original formula.